Now that we have a grasp of how the syntax of quantifiers work, we can turn to their semantics. In general, this is pretty straightforward. A sentence like all f's are G is true just in case if there are any f's, then they're G. And a sentence like some f is G is true just in case there's at least one f which is G. In this video, we discuss these semantics in greater detail and also see how universals work in a way that enables them to be vacuously true, which is to say, true if the objects they describe just don't exist at all. Turning then to the semantics for the quantifiers, we want to see under what conditions a quantified sentence, that is to say, a quantified with no free variables, is true. In order to understand this, we have to begin with the notion of satisfaction. So suppose we have a with a free variable and we want to talk about the things that satisfy it. Say x is large. So suppose we have an object over here, a cube, and we want to know, does this object satisfy the with large x? Well, what we do is we give this cube a name, call it c, and we plug the constant c in for the instance of the variable. If this newly formed sentence comes out true, then we can say that this object satisfies it, or if it comes out false, we can say it doesn't satisfy it. Likewise, we can ask whether this item satisfies cube x, and because it's a cube, it obviously does, because if we replace the variable with the name for the cube, the constant c, then this will also come out true. Accordingly, if by our rules discussed in the last video, we string these together as a conjunction, then the object in question will satisfy this whole well-formed formula. So this conjunctive string will come out true, and that means that this cube also satisfies this whole well-formed formula, x is large and x is a cube. What this in effect means is that we have to be able to replace any variable with a constant in order to find out what satisfies it, and what that means is that all of our objects in question have to be, at least in principle, nameable. There are basically two ways of getting around this. One is to have an inexhaustible supply of constants. We have to have an inexhaustible supply of constants so that we could, in principle, name any object in the domain. Whether or not all those objects gets named is a question we have to make up our minds about. We can either say that everything gets named, or we can say that at least in principle anything can be named. And if, again, taking that name, that constant, and replacing the variables with that constant renders a true sentence, then we can say that the object in question satisfies the formula. And so that's our notion of satisfaction. Now we have one more notion to define before we turn to the semantics for our quantifiers, and this is the notion of a domain. And basically this is just the universe of discourse, or all the objects being discussed. And we require for classical logic that the domain be non-empty. That is to say that at least something must exist. There is, by the way, a philosophical question to be asked here about logic requiring that things exist. So if you're puzzled about that, or you think there's more exploring to do, you're right. Now that we've got these notions in mind, we can provide semantics for our quantifiers, which are going to be pretty straightforward. Starting with the universal, we can say that for all x, Sx is true if and only if the well-formed formula Sx is satisfied by every object in the domain. And for all x, Sx is false otherwise. Conversely, a sentence of the form there exists an x such that Sx is true if and only if the well-formed formula Sx is satisfied by at least one object in the domain, or by some object in the domain, construed as at least one, and it's false otherwise. And there you have it. There is our semantics for our quantifiers, given in terms of satisfaction of a well-formed formula by an object in a non-empty domain, that is to say, the universe of things under discussion.